All right. Now, the next piece up here is taking K to the next level. What else can you do with K beyond just interpret that? We're going to talk about how K is applied in the gas phase. We're going to talk about algebra with K, basically a Hess's law type trick to figure out 1K from the K of other reactions. And we'll also talk about heterogeneous equilibrium. If we have a little bit of time, we'll get into ice boxes as well, but that is content for next week. All right, so the first thing is you can have when you come up with K, when you determine K, K is based on the concentration. We usually do things in a liquid phase, so that's maybe the concentration in solution. Now, you don't have to do it in the liquid phase. You can do reactions in the gas phase. If you do, you can do it in concentration. You can do moles per liter of gas. That's totally fine. But it's often easier to work with partial pressures when you're in the gas phase than to work with concentrations. And so we have two different Ks here. Kc, which is the K calculated from concentrations, and Kp, which is the equilibrium constant calculated from pressures. What do you think? Are these two Ks the same number? Do you think Kp is equal to Kc? Well, it can be, but more often than not, it's a different number. So we want to try and figure out the relationship. Oh, go for it.
No, that's what I thought. It is not.
Yeah, it usually isn't. Well, that's not true. It often isn't. That's a better way to say it.
Yeah.
It can be the same number. It really depends on the reaction. You guys know a way to relate, say, partial pressures to concentrations? Trick we played with last semester, like when we were looking at density of gases. Well, concentration is moles per liter, right? Moles per volume. And again, pressure, well, pressure is in pressure. Pressure to moles per volume, does that ring any bells? You guys remember the ideal gas law? Ideal gas law, PV equals nRT, is a great way to connect up concentration to pressure. So if I'm in the gas phase, I can get Kc. I can do this for gas phase reactions, or I can relate Kc to another value that'll let me work just in partial pressures. I do that by starting with the ideal gas law, PV equals nRT, and dividing both sides by V. That gives me pressure is equal to moles per volume times RT. Moles per volume is my concentration. So pressure is equal to RT times concentration, again in the gas phase. I can use this trick to rewrite Kp, which if I use the law of mass action is just the partial pressure of the products over the partial pressure of the reactants. But I can substitute in for the pressure of C, pressure of D. I can use the ideal gas law to substitute in RD times the concentration of that material. And then I can say, well, R and T is not going to change for my reaction. I'm going to do my reaction at one temperature. One reagent is to have a different temperature than another reagent. So I can collect all the RTs. I do have to be careful to make sure that I'm raising these things to the power that's equal to the coefficient in the balanced chemical equation. And then I can collect them. In other words, Kp, my equilibrium constant in pressure, is equal to my equilibrium constant in concentration times RT to delta N. Okay, so what's delta N? Delta N is if I collect all of those powers, it's the sum of the powers or the coefficients of my products minus the sum of the powers or the coefficients of my reactants. And so if I've got two reactants turning into two products, delta N is 0, and yeah, Kp is equal to Kc in that case. A lot of cases it's equal. A lot of cases it's not. Maybe I have one reactant turning into 3 products, or 2 products turning into 4, 2 reactants turning into 4 products. You got to be careful about that. But you can always get Kp. You can do calculations in the gas phase using partial pressures instead of concentrations, even if they don't give you Kp, if they give you Kc. Now, I'll tell you right now, the most common mistake people make with using this trick is they reverse Kp and Kc. It can be kind of hard to remember which one came first. Try to remember that we did solutions before we did anything else in this class. The very first chapter was solutions. So you start with solutions. You start with Kc. And if you want to get Kp, you take Kc and you multiply it by RT to the delta N. If you remember to always start with solutions, you won't reverse Kp and Kc in this equation, and you won't make that common mistake of getting the wrong value for Kp, because they may give you Kp and ask you to calculate Kc. But if you remember that Kc always came first, write this expression, find what you want to, what's unknown, solve for that, and then only then plug in your numbers. So this is one trick. You can do equilibrium calculations in the gas phase using partial pressures, using Kp instead of Kc.